As the exoplanet gold rush gathered pace, planet hunting prospectors sought ever more refined methods of sifting their discoveries in an effort to give a future interstellar mission the best possible chance of targeting a world that might actually host life. Having identified a rich new vein of distant planets, the next crucial piece of the puzzle was yet to fall into place. How could a telescope be used to sample the atmosphere?
Looking at a planet's atmosphere far away is the best way we have to find signs of life on another world. Because the gases that life produces, here on Earth actually, imprint in our atmosphere in a very significant way. And so it's just amazing to think that on another world we can do the same.
If you were an alien astronomer studying the planets of the solar system, you would see that there's something very different about the third planet from the sun. You would see that its atmosphere is full of oxygen, even though you would know that the oxygen couldn't possibly be there by geologic processes. There would be other gases, like methane, which also shouldn't be present, and yet there they are. And you would, we think, as we're trying to do ourselves, when we look at other stars, conclude that life was the only possible explanation.
In 2000, David Charbonneau took control of the aging Hubble telescope, charged with a single but daunting objective: to make the first ever observation of an exoplanet's atmosphere. The transit method of exoplanet detection, which Charbonneau had pioneered himself, provided a clue for how to solve the puzzle. Planets orbiting closely to their stars make more frequent transits, and the larger the planet, the easier it is to detect. So Charbonneau turned the Hubble's gaze towards Osiris, a gas giant that transits every 3.5 days.
We had the idea that when the planet passed in front of its star, some of the light from the star would pass through the outer parts of the planet, and then imprinted upon that light would be the fingerprints of whatever atoms or molecules are present in the atmosphere.
Different atoms absorb different light frequencies in the electromagnetic spectrum and allow others to pass through, producing a signature in color.
No one had ever discovered an exoplanet atmosphere. And so we needed a guess as to what atom or molecule would be very prominent, would be the easiest first thing to see. So there were some predictions.
Charbonneau put his money on sodium, the telltale yellow glow of street lamps.
The observations were gathered a few months afterwards, and it took more than a year to carefully analyze the data. No one had ever made this detection before, so we wanted to be absolutely certain that what we were seeing was robust.
After painstakingly probing the data, Charbonneau announced his discovery. The atmosphere around Osiris was indeed rich in sodium. However, this was no second Earth. Named after the Egyptian god of the dead, the gas giant Osiris doesn't even have a solid surface to land on, let alone a climate for life.
What we crave to do is to study the atmosphere of an Earth-like planet. Of course, Earth-like planets are simply much smaller than gas giants, and so it's just much more difficult to detect them and to study their atmospheres.
It's the hurdle that has thwarted planet hunters from the outset. The blinding light of the stars completely overwhelms the smaller exoplanets. The first instrument to solve that problem will hold the key to the exoplanet revolution.
Donc ce télescope va nous permettre de faire un bond en avant dans plusieurs domaines de l'astrophysique, et notamment le domaine des exoplanètes. En effet, il va nous permettre d'aller voir l'atmosphère de ces exoplanètes.
The James Webb Space Telescope is designed to view the heavens like they've never been seen before, making the invisible visible. Its vast honeycomb-like dish of mirrors converges light into the eye of a state-of-the-art infrared camera that astrophysicist Pierre-Olivier Lagage spent 20 years developing.
Un objet, selon sa température, émet dans une longueur d'onde donnée. Par exemple, le Soleil émet dans le domaine visible parce qu'il est très chaud. Si on prend un humain, il est beaucoup plus froid et il va émettre dans une autre longueur d'onde, l'infrarouge moyen. Et c'est pour ça qu'avec une caméra dite thermique ou d'infrarouge moyen, on peut voir les personnes la nuit. On n'a pas besoin de lumière, on voit la chaleur émise par un humain, par exemple, dans l'infrarouge moyen.
The same is true of exoplanets. Observe them in the right wavelength, and they glow in the dark. But for the infrared vision to work, it relies on the truly innovative feature of this telescope. Inside the camera lies James Webb's secret weapon, a kind of mask called a coronagraph.
Mais tu vois, cette forme de masque est très particulière et la lumière de l'étoile arrive là où c'est opaque. Par contre, si tu as un petit objet à côté, une exoplanète par exemple, eh bien la lumière ne va pas avoir exactement le même chemin et va passer dans les trous. Donc après, on va pouvoir avoir la lumière de l'exoplanète sans avoir la lumière de l'étoile. Alors, grâce à ce mode coronographique, on va pouvoir aller voir les exoplanètes en imagerie directe.
The mask of the coronagraph intervenes between the overwhelming light of the star, like an eclipse, allowing the infrared light of the planet to shine through.
On n'a jamais regardé ces exoplanètes dans ce domaine de longueur d'onde, et pourtant c'est un domaine très intéressant pour mesurer la température de ces objets, leur luminosité. On peut aussi voir la composition. Il y a certaines molécules, comme l'ammoniac, qui est dans ce domaine de longueur d'onde. Donc la caractérisation des atmosphères sera un des grands sujets avec cet instrument.
Crucial in the hunt for Earth-like worlds, James Webb is ideally suited for detecting ozone.
Pourquoi de l'ozone? Parce que l'ozone, naturellement, sans vie, sans oxygène, on pense qu'il n'y en a pas. Donc on pense que c'est vraiment quelque chose qui est une trace de vie. Et dans le domaine de l'infrarouge moyen de notre instrument, on a justement cette signature d'ozone.
The James Webb promises to be the missing piece in the planet hunter's arsenal. With its breakthrough ability to view an Earth-like exoplanet directly and to study its atmosphere, the odds of identifying a destination for a future landing mission have never been better.
You know, I can probably imagine what that would feel like better than most people can. I've been sending robotic missions to other planets my whole career, 40 years of this. But I can't imagine what it would feel like. I mean, the problem of getting a spacecraft with that kind of capability to another star is so much harder.
The discoveries of the planet hunters transformed the way we see the universe and posed to explorers like Steve Squires, lead investigator of the Mars rover missions, the next tantalizing question. What if we could reach out to a nearby alien star and search for life on a second Earth? What if we could land on another rocky world with running water and a protective Earth-like atmosphere?
If you could find an Earth-like world that has been around for billions of years, enough time to develop advanced biology, it's had the right conditions all that time, there are all kinds of possibilities. I can't imagine what it would feel like. It's going to be, I mean, it's going to be a shared moment for all of humanity when it happens.